Our topic today is maximum likelihood detection. Specifically, we would talk about the likelihood function and the binary hypothesis. And then we will see the optimum detection in a additive white Gaussian noise channel. Now, we start with the likelihood function first, but before going to the likelihood function, let me recall your previous topic, which is the transformation of a random variable, because we would need that knowledge today to generate the likelihood function. So if you go back to the topic of transformation of random variables, you are familiar with the concept that if you have a random variable, if you have a random variable z, which is in the form of a times some constant times the random variable x plus b, right? And you are given the PDF of this random variable x. You are familiar, you are given the PDF of the random variable x. Suppose this is given, this is given, and you are asked to derive the PDF of z, the PDF of z. So I hope you people can do it. The PDF of z. You can write the PDF of z using the transformation of random variables by directly. I would like the final equation which we derived there. You can write the PDF of z in this form. This is 1 over mod a. Keep in mind this a and b are constants, and you have the random variable x, and for that random variable p of x is already given. So if p of x is given, you can write the PDF of z, in this form. Let me write it here as p of z minus b over a. Now we would let's see with the help of an example that if we are given this p of x, how we can write p of z. So for the simple example, we assume that x is normal, right? X is normal. Suppose x is normal. When we say x is normal, we can write the PDF of x. Keep in mind, in additive white Gaussian noise, you are familiar with the concept of additive white Gaussian noise, where noise is normal, right? Zero mean Gaussian PDF. So when we say x is normal, we would write the PDF of x very similar to the PDF of additive white Gaussian noise, and the PDF of x would be 1 over square root 2 pi sigma square e raised to the power minus x square over 2 sigma square. So this is the PDF of the normal random variable x, the PDF of a normal random variable x. So when this PDF is given, and you are required to write the PDF, of z, you can write this PDF using your knowledge of random variable, transformation of a random variable, and our knowledge says that we can write the PDF of z. We can write the PDF of z by 1 over a right? So you can take any constant a. So let me keep it general. It would be 1 over mod a, and then I have PDF of x computed at z minus b over a, which is given PDF of x computed at z minus b over a. Now I have to write this specifically. I have to write this term specifically, right? Because this is giving you the PDF of z. So let's write this PDF. We can write it in this form: 1 over mod a, and this PDF would be, we would write this PDF with the help of this diagram, this expression, with the help of the above expression. So we can write this PDF with the help of this expression. Now keep in mind, we just need to replace this x by the value which is available here. Just need to replace that value. So if you replace that value, your p, it would become 1 over 2 pi sigma square, right? 1 over 2 pi sigma square, and then e raised to the power negative square of the variable. Now instead of a variable we have z minus b over a, so we need to take the square of this, z minus b over a square, and then in the denominator we have 2 sigma square, so we would have 2 sigma square. So this is the PDF of z. This is the PDF of z, right? This is the PDF of z. This is the PDF of z. Now if I just rearrange the exponent, the terms which appear in this exponent, we can say that the PDF of z is actually equal to 1 over mod a, and this is also constant, 2 pi sigma square, and this is e raised to the power minus z minus b whole square over 2 times a square sigma square. This is the PDF of z, which we can write this PDF in this form. Now we would need this expression. We would need this expression in the to observe the likelihood function. You would need this expression. You can also draw this one. You can also draw this PDF as you are familiar with the Gaussian. If you see the PDF of the white noise, it is given in this form, right? This is the PDF of the white noise. Zero mean Gaussian process has a PDF which looks like this. Now you can see this PDF. Suppose A is 1. Let me keep it simple. Suppose A is 1. So if A is 1, this term will be 1, and here also you will have this term will also be 1, right? So when A is 1, you can replace a square. So let me erase those terms. So when a is 1, when your a is 1, we can erase this one, we can erase this one, right? So we have actually 1 over under the root 2 pi sigma square z minus b square over 2 sigma square. So our expression becomes, our expression when a is 1, our expression becomes like this. Now if you compare it with the expression, generalized expression of the standard Gaussian random variable, it says that this value is the mean. This value B is the mean. Now here the mean is 0 for AWG, the mean is 0, so your expression is just z square over 2 sigma square, right? This exponent becomes z square over 2 sigma square. But if you have certain non-zero mean, it appears over here. It appears over here. So this non-zero mean appearing as B causes a shift of this Gaussian variable to a point B. So it's still Gaussian, because you can see it's still Gaussian, but it is shifted. Now this is standard normal with if the sigma is unity and mean is 0, then you have this PDF, which is the same as the PDF of noise, thermal noise, which is modeled as additive wide Gaussian noise. And if you have a non-zero mean, then sigma may be unity, right? Sigma may be unity, sigma may be 1 here. So if you have a non-zero mean, you just shift this mean to some other value, some value B, which appears here in the expression, in this expression it appears in that exponent. So now having this knowledge, let's start with the likelihood function. But once again, before actually observing the likelihood functions, suppose we are we already have the knowledge of the correlator receiver, right? And you have seen in the correlator that if we want to transmit, suppose we want to transmit binary signals. Suppose we want to transmit binary signals. We want to transmit binary signals to represent for transmission of a sequence of ones and zeros, right? So for a binary one, suppose we are transmitting s of t, and a binary 0 we are transmitting minus s of t. So if you observe this is actually the antipodal, these are known as the antipodal signals. Antipodal signal. Suppose this is the transmitted signal. You can always assume, just for simplicity, you can always assume that suppose this s of t is a pulse. So if s of t is a pulse, right, from 0 to t, suppose this is a pulse with just a unity amplitude. So if s of t is a pulse, you have a binary antipodal signal. So the minus s of t would be a negative pulse, right? It would be a pulse like this, minus s of t, 0 to t. It would be minus 1. So when you transmit the signals, we have seen that in binary phase shift keying, our signals are actually antipodal. They have opposite polarity. So if we choose the basic baseband signal, antipodal signals, we would choose these two pulses. And in this case, your received signal, the noisy received signal is actually equal to either plus or minus s of t plus the noise signal n of t. Now this is your received signal, right? The signal which passes through the additive wide Gaussian noise channel. So you have only the effect of noise, in this received signal. We assume that the channel is ideal, right? The channel response is ideal. When we say the channel response, it's the medium through which the signal passes, which can be wireless channel, which can be wired channel, a twisted pair cable, just the signal which comes from the central office to your home, or it can be a wireless channel, which is actually the wireless medium, or the signal which comes from the base base station to the mobile receiver. So the channel always has an impulse response h of t. The channel always has an impulse response h of t. But for simplicity, we are assuming that when our h of t is just a delta function, when our h of t is just a delta function, delta of t, right? Then our received signal is nothing but the signal, the transmitted signal plus the noise one, because the channel actually behaves as a filter, right? The channel actually behaves as a filter. So when you transmit a signal s of t through the channel, the wireless channel, it has an impulse response, and you get a signal which is s of t convolved with h of t, right? And at the receiver you have another term, the noise term, n of t. You have the term n of t here. But now we are assuming that this h of t is actually delta of t. So when h of t is equal to delta of t, anything convolved with delta of t is the same signal. So your received signal is actually equal to s of t plus n of t. Now we said that we have only the effect of noise in our received signal, and this s of t, this signal, is either plus or minus depending upon a binary 1 and a binary 0. So we have for a binary 1, suppose we are transmitting plus s of t, and for a binary 0 we are transmitting minus s of t. Now when we pass this r of t, this is actually, you can say this is your r of t. When we pass this signal through the correlator, we have seen in the previous lecture that what happens, that when we pass it through the correlator, this correlator gives us an integral out, the output of an integral. So if you closely observe your correlator, it actually matches what is inside this block. It multiplies this with s of t, and then it integrates the result, the correlator, and it gives us the output of this integral, right? The output of this integral. This is actually the correlator. So when you observe your correlator, the output here is the output of the integral, and the output of the integral is just actually this is integrating. If you write the output of this integral, it is just r of t multiplied by s of t and dt, right? The output of the integral. And when we take this output at a specific instant, capital T, so we are actually interested in the received signal. We call it r, just r, because that would be a single value, because now your integral is a definite integral. Observing the sample at this instant means we are observing the output of this integrator at capital T. So our signal R, this should not be called a signal, a value, a sample value. A sample value R is actually this one. This is the sample value. Now, what we have seen in our correlator, that if we put the value of our received signal R of t in this integral 0 to t, you are transmitting either plus or minus s of t. So suppose you are transmitting plus s of t. So your received signal will be s of t and of t, and it is multiplied with this one s of t, and we have dt, right? This is our received signal. Now if you solve this in integral, you will get the square of this signal s square, and then the another integral n of t and s of t. So we can write it as 0 to capital T s of s square of t dt plus 0 to capital T n of t s of t dt. Right? Now you can observe this R. If you observe this R, it is actually equal to the energy of the signal. This is the energy of the signal, and here the term noise. Now your R, the value, the sample value R is actually equal to the energy of the signal, and another term which is the noise term. This noise term is actually Gaussian. This is a Gaussian noise, or we say it's a zero mean Gaussian process. This n is specifically, this n is a zero mean with sigma variance and Gaussian normal. It's normal with mean 0 and variance sigma square. It's a zero mean Gaussian process. Now if you observe here, your R is E plus N, right? So now keep in mind, we assume that we have transmitted S of t. We have transmitted S of t. So we get the value of R here when we transmit S of t. If we transmit minus S of t, then instead of E we would get minus E, right? So we are we are assuming that we have transmitted S of t, and we get the sample value R, which is equal to the energy of the signal plus noise term. Now if you observe your sample value R, you can see that it is now actually in the form of that transformed random variable. Now you compare this one, because we are interested, we have the PDF of noise now. We have the PDF of this term, which is noise term, and we want to find the PDF of R. Now if you see, we have some random process, and we add some constant, because energy of the signal is known, constant. So we are adding some constant energy into some random process, and we are getting a sample value R. This sample value is random. So because this n is random, so if you add something, some constant into some random, you would get a value which is random value. Now what we can do, we would be interested in finding out the PDF of R, right? The PDF of R, and we are given the PDF of N. So from your knowledge of additive wide Gaussian noise channel, the PDF of N is given, right? So let me specifically write the PDF of N. If you see the PDF of N, that is given, and it is 1 over square root 2 pi sigma square e raised to the power minus n square over 2, because sigma square is unity. Sigma, if it is not unity, if sigma square is unity, then you can replace this term. You can replace this term you can replace this term by 1 or just 1. So assuming that our sigma square is unity, we have the noise PDF which is given in this form, right? The noise PDF is given in this form. We are interested in finding out the PDF of R, and we can use the knowledge, we can use the knowledge of the transformation of random variables a x plus b, where we say that this a and b are constants and x is a random variable and its PDF is known. Now we have this case, n is a random variable but its PDF p of n is known, and we are interested in finding out the PDF of R which corresponds to z here. So in if you compare this equation with this one, you can say that your R corresponds to z, your n, now n corresponds to x, a random variable here or a random process here, and a, your a, actually here we have 1 with the n unity, we have a equal to 1 and we have the e in this equation corresponds to b. So these are just by comparing these two equations, right? This equation with this one. So if you compare these two equations, you get these values. And if you have these values, you can write the PDF of R using the knowledge of transformation of random variable, and the PDF of R is actually equal to 1 over 2 pi, or let me write that expression. The PDF of R is actually equal to, you can say the PDF of R is equal to 1 over mod A PDF of noise, PDF of the noise term computed at R minus B over A, right? Z minus B over A. Now you can plug all these values. You can plug all these values here, and you would get the PDF of R. The PDF of R is 1, so we would be left with the PDF of noise, which is computed at R minus B. Instead of B we have E, and here we have just unity 1. Now if you write this PDF, you already have the PDF of the noise. So if you just replace the variable by R minus E there, you would get the PDF of R. Now the PDF of R is 1 over 2 pi and e raised to the power minus R minus E square over 2. Right? This is the PDF of R, the received signal. Now, once we get this PDF, we can always write it. We can always write it in this form, and we can always draw it. Actually, we can always draw it. So, if you are interested in drawing this PDF, it would look like the Gaussian curve, right? But the mean is shifted to E, as can be seen. This mean is shifted to E, which is given here. This is the mean value, right? The mean is shifted to E, and the here we are assuming that sigma is equal to unity, because the noise variance is unity. So here we assume that sigma is equal to unity, and this is R. This is R. The value. These are all the. This is the PDF, the probability density function of R. Now keep in mind, this is the conditional PDF. Why we say it's a conditional PDF? Because here we are assuming that S naught is transmitted, right? Or S of t is transmitted. We are assuming that S of t is transmitted, right? So this is the PDF of R. Let me write it specifically, that this is the PDF of R, given that this lines say means given that the PDF of R, given that S of t is transmitted, right? So this is the conditional PDF of R. We call it the conditional PDF of R. And similarly, we can verify. Similarly, we can verify that if minus S of t is transmitted, if minus S of t is transmitted, we can get the conditional PDF of R. We can get the conditional PDF of R, which would look like this. For minus S, the conditional PDF of R, given that minus S of t is transmitted, it would look, actually before going to the conditional PDF, let me specifically say that when you transmit minus S of t, your R would be equal to minus E plus N, right? This would be R. And if you find out the conditional PDF of R, the P of R, given that minus S of t is transmitted, it would be, you can write it here, PDF of R, given that minus S of t is transmitted, it would be 1 over, I'll write it directly, you can derive it, 1 over 2 pi sigmas. Instead of sigma square, we are writing just unity. So here sigma square should appear if the variance is not given. E raised to the power minus R plus E. It would be plus E whole square over 2. Now this would be the PDF. You can derive it using the same steps. This would be the conditional PDF of R when minus S of t is transmitted, right? So you can draw this PDF. If you want to draw this PDF, it would again appear as a Gaussian curve, and the mean here, now this time the mean is shifted. This is the mean value, right? This one in the expression appears as the mean value. So the mean is shifted to minus E. This point is minus E. So you have PDF of R, given that minus S of t is transmitted. And this is the conditional PDF. This is the conditional PDF of the received sample, this R, the conditional PDF of R when minus S of t is transmitted. Now you have, if you are, let me draw these two PDFs together on a single diagram. So if I draw it on a single diagram, I would say that the PDF of R, we can draw it like this, and let me draw another one, and let me draw this axis. This is R. Now the PDF of R, this is a positive E, and this one is minus E. Now you can clearly see that this is the let me instead of using the term s of t, when we say s of t, suppose which represent a binary 1, suppose this is our s naught, and minus s of t which represent a binary 0, suppose this is our s1, right? Just to be consistent with your previous knowledge of the antipodal signals, that you can always draw antipodal signals as 2 points, which appear on the 2-axis on psi 1 of t, if you go back to your BPSK knowledge. So you have s naught and you have s1, s naught and s1. Now here it should be the other way around, you have s1 here and s naught here, because we are assuming plus signal for the binary one. Now if this is the case, you can say that this is my conditional PDF P of R, given that S of t is transmitted, or let me say given that S naught is transmitted, and this is the PDF of R given that S1 is transmitted. These conditional PDFs are known as the likelihood function. Now this is the likelihood function. PR given S naught is likelihood of S naught. Similarly, P of R given S1 is the likelihood, we call this PDF as the likelihood of S1, S naught and S1. So we have these likelihood functions, right? This is the likelihood function. With this knowledge, these are the conditional PDF, which is the likelihood function. Now, how the detector, decides, take decision. So let's try to have a fresh slide, and I will draw it a bit more accurately. I'm trying to draw it more accurately. So with this fresh slide, suppose we have these two conditional PDFs, right? We have these two conditional PDFs. Okay, let me draw it here. This is my axis R, and this point, suppose this is, I represent this point by gamma, right? I represent this point by gamma. Now let me draw it correctly. I represent this point by gamma. Now let's discuss this with the help of this diagram, the process of detection and the hypothesis. The process of detection and the hypothesis. Now suppose we receive the signal R. We receive the signal R, which is the signal R, which is a point over. Suppose we have received some value here. This is a sample value, the value of R. The value of R, which is here. It may be any value on this axis, right? Because we have PDF of R given that S naught is transmitted, and the likelihood function PDF of R given that S1 is transmitted. We have these two PDFs available. So the value of R can be any value on this axis. Suppose this is, we received this value, which we assume for the time being that suppose we received this value. Now the detector has to decide whether it is S0 or S1. Now let me recall, our mean values are here. This is E, the mean, and this is minus E. As we have seen that R is equal to E plus N when S naught is transmitted. When S naught is transmitted, then the value of R is E plus N. Now suppose this value of R is, we have received this value of R, which is E plus N. The detector has to decide in favor of, the detector has to decide whether S naught is transmitted or S1 is transmitted based on these likelihood functions. Now we are the likelihood functions are available with us because we know the noise is zero mean Gaussian, and we can plot this conditional PDF or the likelihood function for S0 and S1. Now when S0 is transmitted, we would get R, which is equal to this one, and it can be this value of R, it can be any value on this real axis, it can be any value on this real axis. This is a real axis, right? So it can be any value from minus infinity to plus infinity. It can be any value on this real axis. Suppose we have received this value. Now you can clearly see that this value, if we project it to on the vertical axis, let me draw the vertical line here. Let me draw the vertical line from this point, and this vertical line intersects both the PDFs, this one here and this one here, both the likelihood functions. Suppose this is L1 and this point is L2. Now you can clearly see that the signal, the sample value which we observe, it belongs to, we don't know actually, the receiver, although at the transmitting end we have the knowledge that we have transmitted S0, but the receiver, the detector has to decide based on this value of R and having the knowledge of the likelihood function. Once you have the knowledge of the likelihood function, based on this knowledge, the receiver has to declare whether it is S0 or S1. Now this particular value intersects both the likelihood function, and we can see that the PDF of R given S0 is the value here, this intersection value is L1, smaller than the intersection value here, and this value represent the probability density. On the vertical axis we have the probability density, or we can say the probability that this sample value belongs to this PDF, or this sample value belongs to this PDF, the likelihood function. So these two values L1 and L2, specifically L1, the value L1, the value L1 represents this gives you the knowledge that L1 gives you the knowledge that the sample value, the sample value belongs to the conditional PDF PR given S1, this likelihood function. The sample value belongs to this function, and the L2, if you observe L2, L2 gives you the knowledge that the sample value belongs to R given S0. Now L1 and L2 are the probabilities. We can clearly see that L2, in this case, we can see that L2 is greater, L2 is greater than L1, which means that the probability that the sample value of R, the probability that the sample value of R belongs to S naught, belongs to this likelihood function, PDF of R given S naught, this probability is greater than the probability of L1. That is the probability that this value belongs to S naught. Or in other words, we say the likelihood that the sample value of R belongs to the this likelihood function, it is greater, the likelihood is greater than the likelihood that it belongs to PR given S naught, right? So this is what L2 is greater. The L2 is greater than, let me specifically, L2 is greater than L1. So the likelihood that this is S naught is more than the likelihood that it is S1, right? So we would say that the based on the likelihood function which we have just seen in our diagram, based on the likelihood function, we would decide based on the likelihood function, we would decide that this point actually belongs to this likelihood function PR given S naught. Why? Because L2 it is more probable that this received signal R is represent S naught. This received signal R represent S naught then S1, right? This received signal may represent S1, but its probability is low, L1. So let me write it. The received signal R represents, or the received signal R is S naught, represent S naught, or let me say represents S naught. The received signal R represents S naught with probability L2, and the received signal R represents S1 with probability L1. Clearly L2 is greater than L1, so it's more likely that the received sample value is S naught. So it is more likely, let me write it. It is more likely that the received signal R of t, it is more likely that the received signal R of t represents S naught of t. Or you can say it is more likely that the received sample value R represent S naught, because your L2 is greater than L1. So based on the likelihood function, our likelihood detector would decide in favor of S naught. Our likelihood detector likelihood detector would declare that S naught is transmitted. S naught is transmitted, right? S naught is transmitted. Now, if you observe your likelihood function, let me redraw those likelihood function, and we summarize our discussion. Let me redraw that likelihood function. Based on the knowledge of our likelihood function, we say this is E, this is minus E, and this is the value which we receive, the value of R which we received, and this is our gamma, right? This is our gamma. So the value of R which we received is this sample value, and we said that this sample value actually cuts these two axes on L1. This is L1 and this is L2, right? Now, this, if we discuss in the terms of pure statistical terms, we say that we have a received sample value. And that received sample value R, it may belong to, we have the conditional PDF PR given S naught, or these likelihood function PR given S1. So we have this these likelihood function. We have a received sample value. Now we say that this receives, we have two hypotheses about this received sample value. Now we have two hypotheses. That is why we called initially, we start with the binary hypothesis. We say the binary hypothesis. So we have two hypotheses about this R. One hypothesis, we can say that this R can be S naught, or this R can be S1. So we have two hypotheses, binary hypothesis. Suppose we say that this is our hypothesis, hypothesis H naught. Our hypothesis H naught says that R is S naught. And hypothesis H1, this is our hypothesis H1, which states that the received sample value is S1. Now, based on this value, we can compare the received value with this threshold. We have the threshold available, and we can say that if the received value is greater than this threshold, let me draw this threshold. Let me give it a different name, because you would mix it up. Let me give it a different name. Let me modify this one. The threshold, let me define this threshold as eta. So this eta is a threshold. This is a value, some value. So this received, we have two hypotheses. If the received signal is greater than the threshold eta, H naught is true. We say hypothesis H naught is true. And if the received signal is less than this threshold, we say hypothesis H1 is true. which simply means that if the sample value is greater than the threshold, then the receiver would declare based on the likelihood function that S naught is transmitted, or a hypothesis H naught is true. If the received signal, if the received signal is less than this threshold, then it means that S1 is transmitted and hypothesis H1 is true, because these are the two hypotheses about this sample value. We observe a sample value and we have binary hypothesis. This sample value can be S0, this can represent S1. Now hypothesis H0 says that the sample value is S0, and hypothesis H1 says that the sample value is S1 according to hypothesis H1. Now because the sample value R is greater than the threshold, so for the sample value greater than the threshold, H0 is true. If the sample value is greater than the threshold, H0 is true. If the sample value is less than the threshold, H1 is true. Right? These two hypotheses. This is how we test the hypothesis. We observe the sample value. If it is greater than threshold, we say H0 is true. H0 says that the received signal is S0, represent S0. When the received sample value is less than the threshold, hypothesis H1 is true, and H1 hypothesis says that the received signal represent S1. Right? And you can clearly see from this figure that this likelihood functions. Now you can clearly see from this likelihood functions that if the received signal falls over here towards the right side of this threshold, for all the points towards the right side of this threshold, this may be here, it may be here, it may be here, it may be here, L2 would be greater than L1. For all these points, L2 would be greater than L1, which means the hypothesis H0 is true, or the received signal represents S0. Right? For all those points which are towards the left of this threshold, all these points, you can always project a single point. Suppose I project this point vertically. So you can always project these points. Now, for all those points which are towards the left, L1, the likelihood, this likelihood is more than this value. You can always project and see. It's more likely that this sample value intersects both the PDF at these two values, and now the likelihood for this particular point, this probability is greater than this probability. So it means it is more probable that this signal point belongs to this PDF. P of R given this likelihood function, P of R given S1, or the hypothesis H1 is true. So this is how the hypotheses are tested. This is for the binary hypotheses are tested, and we have a threshold. We have a threshold available for binary hypothesis. We learn the binary hypothesis because the most of the time you would see that the different modulation schemes, specifically the quadrature amplitude modulation scheme, it requires the binary hypothesis. It requires the knowledge. It requires the fundamental knowledge of the binary hypothesis. So these conditional, keep in mind, these conditional probability density functions are known as the likelihood function. So we have likelihood function PR given S0 and PR given S1, and we write the binary hypothesis. We write the binary hypothesis for our received signal R, and we jointly write this with using this threshold that H0 is true when it is greater than the unity, and this threshold, not unity, this threshold, and H1 is true when it is less than this threshold. The received signal is less than this threshold. So a binary hypothesis is jointly written in this form. So this is our binary hypothesis. And the optimum detector or the maximum likelihood detector, take decision on the basis of the likelihood available on the basis of this these likelihood function. The likelihood detector would decide based on these likelihood function and the knowledge available. So the real sample value would be compared with the threshold, and the likelihood is observed. If the likelihood is for S naught is greater, then the optimum detector would declare that S naught is transmitted. If the likelihood of S1 is detector, S1 is greater as for this sample, then the maximum likelihood detector would declare that S1 is transmitted. So this is how the maximum likelihood detection takes place at the communication receiver. And this maximum likelihood detection or the maximum likelihood detector is actually the optimum detector in additive wide Gaussian noise. This is known as the optimum detector in additive wide Gaussian noise.